everyone, and welcome to our second webinar at GW Spatial. This is a special webinar about a coordinate system for the city of the future. A little bit about GW Spatial. It was founded in 2011. We provide software development and professional services for the administration, analysis, and visualization of spatial data. Our main areas of interest are high-precision cartography, exploration, and energy. Some tips for this session. To avoid outages, close bandwidth-intensive apps. This webinar will be recorded so you can rewatch it whenever you need. Do not wait until the end for the end of the session to ask. Instead, you can leave your questions in the chat box on your screen. Our agenda for today is the geographical patterns and features of planned cities, the reference system challenges for the line, existing transportation corridor use, and the benefits of a single coordinate system. And with this, I'll pass it over to you, Richard.
Thank you, Claudia. My name is Richard Nava. I'm a cartographer and president at GW. I've been involved with coordinate systems, low distortion projections since about 2007. I've also ported the original Fortran code to ArcGIS and software that we use here at GW for designing coordinate systems. And we've been working with several states here in the US while developing these coordinate systems for inclusion into the State Plane Coordinate System of 2022, which should be released some point in 2025. In general, I contribute with scientific software development at GW. Now, one of the first topic of our conversation today is about what we call the planned cities of the future. Really, we're focusing on a particular city that they call the line. But we want to take a look into some of the features and some of the characteristics of planned cities in general, so that we can then make a transition and see what this line is all about and how, spatial reference systems and the challenges that, confront them once you want to design something for that big span of geographical area. And also, we're going to be using a use case that we already worked on here at GW so that we can make some parallels to see and maybe see what we can envision will happen for a coordinate system for that particular city or planned city. So in general, a planned city is a city that did not grow organically. Typical growth that happens when settlement starts at a particular location. It starts growing to the sides. A planned city is a community that was planned in advance. Essentially, the undeveloped land, the built environment is actually planned on this undeveloped land, and you have to take into account during the design different things like water, where's the water going to come from, solar coverage for that particular area, transportation, utility networks, and distribution networks in general, where the goods are going to come from if it's close to a larger city or something like that. So a lot of things to take into consideration. And what you end up with then is these urban areas that have very specific and very notable patterns, right? Here we have several examples that we acquired from looking up these different cities. And the first one is, I think this is the most interesting one as far as the shape of it is Brazil. In Brazil, there's a city called Brasilia, and it has the shape of a bird. Many different sources call it a different shape, but a lot of them call it a bird. So we're going to go with bird. There are also many others across the world. We have one in Australia, Italy, Chile. Washington, D.C. is also a planned city. And a lot of the shapes here, you can start to see a lot of them are radial, central feature, and then networks of transportation radiate from there, or a grid. A grid pattern is also very common. In El Salvador, Chile, we have that radial, semi-radial pattern there on the top. So different shapes, but most of them, I think, are sort of like square, or circular, semicircular, semi-square, not too much elongation to them. And that is something that we really pay attention to whenever we're designing coordinate systems, right? If we're talking about a coordinate system for the city of the future, it's a planned city. And these other planned cities that we're looking at, they have about a 1 to 40 kilometer long axis, right? So their elongation typically spans about maximum 40 kilometers. And another feature that we consider whenever we're talking about reference systems and coordinate system for these geographical areas is the minimum, the height, the elevation change between points on the city, which for most of the cities that we just saw, it's minimal, right? It's something that, because they're square, they're sort of relatively flat areas, we have minimal change. So not too long axis, and especially compared to what we're going to see here in a little bit, and just minimal elevation change. Now, the reason that is important is because when we're working with spatial data, right, we are planning a city of the future. We're designing the city on paper, and we're trying to, see how we're going to work it, where we're going to place things. During all this planning and, the architecture that goes in, then follows construction, right? And for construction, then we're going to have land surveyors, civil engineers doing design and staking out those points on the ground. And all of that comes from design software, engineering software, where we have all this plan that we're going to execute on the ground. So we need a spatial reference system for that, because we do plane surveying, because we have X and Y, northings and eastings that we need to design with to finally go out and stake out on the ground. So we need a spatial reference system. Now, there are many different spatial reference systems that different disciplines use, depending on what they're trying to achieve. Surveyors and engineers are pretty common on using low distortion, scale to ground, ground coordinates. They want ground coordinates on their map, so that whenever they transfer a design to the ground, those distances that they saw on the design, on the software, on the map, are going to be as close as possible to the actual distances on the ground. Now, other disciplines like mapping and social economic activities that are planned are typically done with a reference system that does not take too much that ground distance into account. It's more like getting all the data into a single system and doing some analysis on it and planning on it. But if we can have all these disciplines working in a single coordinate system, I think that would probably be the most ideal situation. So whenever we're talking about a planned city, then it is possible to talk about a planned reference system, right? When projects start evolving organically, we might not have the chance to design a system for it, but if the city itself is being planned, then we have a better chance of having a reference system for the entire thing, or reduce the amount of reference systems that are used between disciplines. And whenever we're talking about, let's plan a reference system, let's plan a plane that we can use to, have our X and Ys and our northings and eastings for this area. The first thing that we run into is the Earth's curvature. The larger the span of the area, the more the Earth's curvature is going to be, or is going to play a role. So in this case, we see a diagram here of a typical map projection concept, right? We have a source of light near the center of the Earth, and then rays are projected from that center, and as they open up radially outwards, you can start to see how the features, in this case the ellipsoid or the Earth, get projected onto the plane. For example, here where the projection surface is cutting through, we have the grid length or the map length less than the ellipsoid length. So there's distortion, right? The distances on the ellipsoid are going to be larger than those on the map. And whenever the plane is cutting above the ellipsoid, then we'll have larger distances on the map and shorter distances on the ellipsoid or Earth. So this is a typical concept, of linear distortion and how it happens. Now we have the added characteristic of that we're not working on the ellipsoid, we're actually working at ground. So this effect is magnified if the ground is way above that projection surface. So we have that same line, that map projection, like UTM state plane that is cutting through the Earth. and we have our project area right here. We measure things, we measure points on the project area, and we end up with larger distances on the ground that we see on the map. So the grid length or the map length, in this case, both of these situations is going to be less than that on the ground. So we have now the Earth's curvature and the ground taking into account, and we see how this impacts the distortion, which is the difference in distance between the ground and the map. Now, we're going to switch into the next topic, which is the line, right? The reference system challenges for the line. The line is a linear city in Saudi Arabia. It's in development. We don't know too much about it, besides the fact that it has 170 kilometers in length, and it traverses through these 4 types of environment. We have the coastal desert, the mountains, and the upper valley. Now, we were talking about span or length, the 170 kilometers. We were looking at 40 kilometers max for those other planned cities. This one is way larger, right, as far as linear length. And then we also have the added characteristic of the height change, right? We don't know exactly what it is here. We haven't done the analysis, but we can see that it is not necessarily a flat area, right? We see coast, we see mountains, we see upper valley. We can assume that there will be some height change, considerably more than what we see in the other planned cities. Now, about the line itself, it's supposed to be, eco-friendly, just open environment, and no cars, no streets, no carbon emissions, which is pretty different from what we see in most cities right now. So everything is supposed to be more open spaces, parks, gardens, the natural environment. If you think about if you were to be in this city that it's linear, as soon as you start moving perpendicular to it, because it's thin and elongated, you will actually reach nature faster, right? The open space faster than in a regular city, which is more like a square or a circle, right? So that's one of the benefits. And I think that's where they're going with for moving fast into the natural environment. They're also talking about 100% renewable energy, self-sufficient communities, 5-minute walk to daily needs, and the utility and transportation below the surface. And this is the one that we're most interested in talking about today. We're talking about ultra-high-speed mass transit underneath the surface, which is pretty interesting because it's a really large span of land. Now, this is a diagram that they have on their neon.com website for the line. Basically, we have that pedestrian layer up top, which is where all the people interact and have that 5-minute walk to most essential daily needs. Then we have a middle layer, which is a service layer. Imagine this as the trucks that move different goods to restaurants, for example, downtown, where you would typically have a walk and stop at a restaurant, and then you see this truck that is unloading, the raw material. And then you have the spine layer, which is the transportation network or line. This is not so much a network as it is a line. And the next generation freight. Now, this is supposed to be artificially intelligent controlled so that, you can have ultra high speed. I don't know exactly what the speed is, but ultra high speed sounds way more than what we see on the surface. Now, once you start looking at a transportation system that runs linearly like this, then you'll start to think about, if you want to design a reference system for it, you'll start to think about the curvature of the Earth and your ground, right? Your height change, elevation change between the different areas of that line. And low distortion projections are coordinate systems that have a map projection that is designed or placed at a particular location on Earth so that the ground distance is as similar as possible to what you find on the map or on your design software. So here in this diagram, we can actually see that the projection is placed right in the middle of the project horizontally. And we actually have a representative ellipsoid height for that project if we were to work within this middle area here on the ground. We then stick a projection surface right through the middle of that, and we end up with this height limits, right? This limits where we see here covered in green, where we have low distortion because the projection surface that is cutting through is really close to the ground. And this is very important because surveyors and engineers, they want to work at ground. They want to be as close as possible to the ground. So whatever they design on their software is actually as close as possible in distances and length to the ground, because they keep measuring on the ground, bringing into software, designing, and then staking out on the ground again. So back and forth between the ground and the design software. So you want those two surfaces as close as possible, the projection surfaces and the ground surface. So, and this is what we do with low distortion projection coordinate systems. Now, the best way to illustrate this is with an existing use case. And we did this for a transportation corridor. And the transportation corridor itself, it's about 430 miles, 60 miles. And it's about 4 times the length of the line of that city. It runs from Washington, D.C. to Boston. And it has 2 branches to Harrisburg and Springfield. And basically, we have high-speed trains that run through the main line. And we have those other 2 branches that are part of the corridor and need to be taken into consideration. Now, another important aspect of this is not so much the high-speed train of transportation, is that the project managers, the corridor managers actually, are working with LiDAR data. They're actually collecting highly precise point clouds, either by navigating through tunnels terrestrially or aerially by flying drones and aerial vehicles to collect all this data. And they're doing this for the entire corridor, so the 400 plus miles of data that need to be registered one with the other, as they progress through the entire length of the area. They're also using high precision or high accuracy course networks, so continuously operating reference stations, GPS stations that are scattered throughout the corridor that are observing satellites 24 hours and are obtaining geodetic coordinates that are then adjusted for the entire network in real time. So they get very, very precise coordinate information for each one of those stations. So they have this network of control that is adjusted in real time, that is highly accurate geodetic control, that they can reference any sort of work to, so that they can have good coordinates. Using also data that is highly precise from point clouds that are collected with millimeter accuracy or millimeter precision. And they're combining these and then putting them into a projection that will introduce linear distortion. So the projection itself will distort the distances from those on the ground. So that becomes a problem. Now, that distortion then we talked about is the difference between the grid and the ground, right? So basically, it's a ratio of distorted length between, the distorted length to true length on the ground. And usually we quantify or we express it as feet per mile or millimeter per kilometer, which is parts per million. So millimeter per kilometer equals parts per million. And the distortion can be negative or positive. When it's negative, the map length is less than the true distance on the ground. And when it's positive, the map length is greater than the true distance on the ground. And this table kind of helps us see where we are when we talk about low distortion. Basically, we want to stay within the 10 and 40 parts per million. Most projects that we work on are plus or minus 20 part per million range. We want to stay within that range, which is 1/10 of a foot per mile or 2 centimeters per kilometer. This can also be expressed as a ratio. So we can say 1 in 50,000 for a particular area. Now, this is the original situation that we had. We have the corridor intersecting 9 state plane zones. So the state plane system, it's in the US and it's published, and people can select each of those zones from their data collectors or their software, be it in surveying, civil engineering, mapping, whatever software usually has the US state plane system incorporated into it so that people can work on published systems that they can share data with other agencies, other companies, and have them understand what what the data is. So we have common systems that we can share between us so that our data can flow without the need of transformations or not knowing what reference system was used. So it's available for everybody, so everybody can select them. Now, here we have a map with the distortion for 9 state plane zones that it intersects. And basically what we're looking for, just talking about low distortion in the parts per million, we're looking for 20 parts per million, which is green. So you see that as we start moving from Washington, we have higher distortion, -40 plus 60 parts per million. Then we get into pretty good area for the green, but then we change zones, and then we start good with green, and then we start getting more distortion with another zone, and you can start to see inconsistencies, right? As we go along this corridor, and also if we were to use a a system for a project that spans several coordinate systems, measure across an entire length of a railroad, we will start to get into the situation where which coordinate system are we going to use? Because we need that plane. We need the X and Y, right? The northings and eastings. So which one? And that becomes the problem for the project managers. We're like, how do you ask people which zoner they're going to use? So let's say that, all right, let's worry about just a single system. We won't worry about the distortion right now. We'll worry about getting all the data in a single system. So at UTM zone, UTM zones are available in that area. 18 North is the specific zone for this particular area. And let's say that we want to start working on this, we see right away that we have a problem with distortion. So the larger the system or a single system that we're using, the more serious the problem with distortion. As you can see here, the 20 parts per million that we were looking at, which we consider is pretty good, it's pretty low. It's limited. It's just in limited areas here on the sides, right? So just not even, I don't know, 10%, less than 10% of our railroad line falls within those limits. So most of it, like, for example, if we're working in Philadelphia, we might have several feet per mile distortion. So if we were to measure a mile, we will have several feet plus or minus distortion on it. So this is the actual result. This is the actual design that helped us accomplish what we wanted. We have a high-speed line that is running through the main line, right? So the main line has the high-speed trains, and then we have the two branches. So what we want is to have that low distortion plus or minus 20 parts per million across the main line that runs from Washington to Boston. So this is how we did it. And this is how you would quantify it statistically, of course. We have the main line, plus or minus 20 parts per million, 100%. Then we have Harrisburg, which runs a little bit into topography. So we have this variance now where we have minus 20 to plus 60 parts per million. But we see a good chunk of coverage in the plus or minus 20 parts per million. And then Springfield also runs a little bit into a little bit of topography. So we have plus 20 to plus 40. About 15% of the line. We could do better in Harrisburg or Springfield, but we wanted to do really, really good on the main line. So we actually worked the entire thing so that we could get really good results on the main line, which you can see here. We have a profile, so like a vertical profile, where we have the parts per million here on the y-axis, and then we have the distance in miles on the x-axis. As you can see, as we start moving across the entire length of the main corridor, we start to see that we're really close to the 20 here, but then we go down almost, well, to 0. And then we stay within the plus or minus 10 parts per million, which is 0.5 feet per mile, or 1 centimeter per kilometer. So this is pretty good. This is pretty nice overall. We get pretty good performance. I mean, we do stay within the plus or minus 20 parts per million. So, the high speed trains and the work that is done engineering-wise, design-wise, can actually be pretty accurate and precise. So we're using the course network to have this geodetic coordinates. We're using the scan data, which is 2 millimeter precision for most instruments. And now we have a low distortion projection so that when we're working on X, Y, northeast and eastings, we can actually have the least amount of distortion possible going from the ground and to the ground. Software, ground, software. Now, as you can see, those are the benefits, right? We get a system that is as large as possible, right? Because we're actually looking at how it's performing. So it's optimized, right? So we can cover the largest area possible with the least amount of distortion. This increases our chances of using a single system. Now for the line, we don't know if it's going to be a single system. We haven't done the analysis, but doing the actual analysis of the distortion of the heights and all this, we can actually increase our chances of having a single system for the entire length of the project. So it is the best replacement for your typical workflows that involve site calibrations or state plane modifications, right? When you hit your data collector and hit the here button, and then your existing state plane that is cutting through the ellipsoid gets scaled up to the ground, you don't know exactly how it's oriented. You know that you probably get pretty good coordinates, at least distortion in that particular area where you calibrated to, but you don't know beyond those limits how it's going to be performing. So with this LDP design process, we can actually see all that, and we get well-documented coordinate systems that are compatible with all software, the majority of software at least. And the distortion is quantified so we can see what is going on. We have these profiles, we have this coverage that we just saw, and it's optimized for the largest area possible so that we can have a single system, for example, on the Northeast corridor instead of those 9, 10 systems with UTM. Now, the main goal here is so that the distances on the CAD, surveying, mapping software are as close as possible to the distances on the ground. We give this coordinate system to engineering, surveying, GIS professionals, or planning, and it's all compatible with all the disciplines. They can all input into their system via a PRJ file or projection definition numbers that they can input. The definition is usually clean so that they don't have no trouble inputting the numbers, and they can all work in a best performing way possible. And with this, I'm gonna finalize. I wanna thank you very much for your time today. And I'm gonna give it back to Claudia so she can help us with any questions that might have come up. Thank you very much again.
All right, I'm just gonna wait a minute to see if any last minute questions come up, and if not, I think we can wrap it up.
All right, I think I did pretty good. So no questions. Go ahead, Claudia.
All right. Well, I want to thank you everyone for joining us in this session. For more content on what we do at GW Spatial, you can follow us at LinkedIn. And also, if you have any questions that may come up while rewatching the session, you can send an email to connect@gw.us, and we will make sure we can answer them. Again, thank you so much for joining us. Have a good day.